Hi, this is Ivan from iC-Haus. Very happy to talk to you today about Rotary Encoders, in particular how our next generation system-on-chip devices boost your application, especially in terms of performance and flexibility. Well, before I dive into the latest and greatest features and developments, I'd like to give you a quite high-level overview of the sensor technologies that are around, giving a short comparison of these and explaining a little the motivation we had in mind when developing our next-gen SoCs. So let's get started. What is around? We have magnetic scanning. There you have a magnetic pole wheel with some magnetic pole pairs on it, and the magnetic field is scanned by a sensor chip. The sensor technology might be Hall-based scanning or XMR technology, so magnetoresistive. Then there is inductive. Inductive consists of a rotor with some metal elements on it, and on the opposite side there is a coil PCB, which consists of a transmitter coil that provides an electromagnetic field that is modulated by the metal elements of the rotor and then picked up again by the receiver coils. This amplitude modulated signal is then demodulated, so the carrier frequency is removed, and remaining is a sine-cosine signal, which we love when working in encoding. Going to the optical domain, there is optical reflective with a system on chip with an integrated LED plus the photodetectors, so the transmitter and the receiver is integrated in one package. The LED illuminates a code disk. The reflective structures on the code disk provide a projection, reflect back a projection for the photodetectors. Last but not least, there is classic optical transmissive encoding, where you do have the LED on the opposite side of the photodetectors. In between is a code disk with slits or a mask, and that shadow projection is then received by the photodetectors. So here is a pretty high-level comparison of the sensor technologies that I just showed. I don't want to go too much into detail. Well, there certainly are pros and cons for all these technologies. That's why they are around, right? But I'd like to use this table to somewhat explain a little the motivation we had in mind when developing our next-gen SoC devices. So looking at the magnetic side of things, magnetic off-axis encoder solutions have been quite popular, especially in integrated encoders. Why that is the case? Well, they are easy to install, they are very flexible in design and size, and they are robust in operation. They can be used in harsh environments, for example. But some applications, they might just demand a high resolution and accuracy. And that's exactly what we wanted to tackle as one of our main motivations. We want to increase the resolution and accuracy of these magnetic off-axis encoder solutions. Looking at the other side of the resolution spectrum, there is high-end optical transmissive encoding. Well, we have achieved the 25 bits of angular resolution long before, but that came with a price, the price of tight assembly, precise mechanics, and a clean house working environment. And that's exactly what we wanted to change. So we want to improve the robustness and ease of installation for these high-end optical encoder devices. On the next couple of slides, I am very excited to present you the two new encoder innovations that we have developed. I will be starting with the optical one. So here it is, the new iC-RT2624, which is a high-resolution optical transmissive encoder SoC. Let's check it out. So the iC-RT2624 comes in a 7x5mm opto-QFN package with 38 pins. Operating voltage is from 3 to 5.5 volts, temperature range from -40 to 125 degrees C. Sensor technology, well, it's optical transmissive, so there is an LED required on the opposite side of the photodetectors. And it's absolute. It's absolute by turn-on, so right after startup, the angle information is available. There is no motion required whatsoever. It's a two-track scanning system. It scans a pseudorandom code, a PRC, to find a core's absolute position. And then the incremental track is further interpolated on chip to increase the resolution. Key applications, well, obviously, high-end optical transmissive encoders, rotary encoders in a sealed housing, but also modular kit-style bearingless encoders that can be integrated in servo motors, for example. When it comes to features, you can achieve outstanding resolution and accuracy with this device. So a 26mm code disk will be resolved with 26 bits of angle information. To further increase the accuracy, there is an on-chip eccentricity correction that compensates for the typical radial runout of the code disk. As I said in the beginning, one of the main motivations was to improve in terms of robustness and ease of installation of these high-end optical encoder devices. That's why we have integrated a contamination-resistant and robust scanner front end. What does that mean? This chip does oversampling and even bit error correction, so that the position generation of this device is extremely reliable, even if there are some particles in the system. When it comes to encoder design and size of the code disk, this chip is very flexible. So thanks to the flex code feature, any code disk diameter can be designed from 20mm outer diameter. One of the unique points certainly is the high mechanical alignment tolerances. And I'm happy to show you some numbers on the next slide. There's a wide variety of interfaces integrated in this chip. All of these interfaces that you see here are available simultaneously on dedicated pins. So the absolute position information can be obtained by BIS, SSI, or SVI, whereas there is a quadrature output that is flexible, programmable in terms of AB resolution. We call that flex count. In addition, there are two differential sine cosine ports. One is the classic analog signal path that is designed in a safety-ready fashion, and it provides a resolution from the code disk. So the number of lines of the code disk are here output as sine cosine signals. And then there is an additional sine cosine generated that uses a DAC, so the internal absolute position converted to an analog signal with a programmable output resolution. So independent of the code disk size and native resolution, you can now just program the 2048 CPR, for example. As I said, one of the unique features of this device is its high mechanical alignment tolerances. From sensor to code disk, in tangential direction, there's a tolerance of plus minus 0.5 millimeter. In radial direction, there's also a tolerance of plus minus 0.5 millimeter. And we can even allow some tilt. Also very important is the air gap. So the distance between the sensor package surface and the code disk. Imagine you have a bit of axial play in your system, or there is thermal expansion of the shaft, for example. That's what you want to compensate inside your encoder system. So the air gap tolerance of this device is up to 0.8 millimeter. That's the Z1 here. So 800 microns. And the full tolerance range is also available in operation due to the integrated LED power control that keeps track of the optimal operating point of the illumination, and also the dynamic outer adjustments that can be enabled inside this SoC. When it comes to flexibility in encoder design and size, this is where the iC-RT2624 really shines. So there is a standard code disk with 26mm outer diameter and 1024 lines on the code disk. Here you can see the close-up of the two tracks. So the inner track is the pseudorandom code, and the outer track is the incremental track that is further interpolated on chip. But when it comes to scaling the size of this code disk, the chip can do anything from 20 millimeter outer diameter to like any code disk size that is required by the application. And the best part of it is independently of the native resolution of the code disk, so the number of lines that are on the code disk design, the output resolution is just programmable. So you can program the bits for the angle resolution for BIS and SSI, but you can also program the CPR, so the resolution for sine cosine output due to the sine cosine generator, and the number of pulses that are output per revolution on the ABZ quadrature interface. So that was our new innovation in terms of high-end optical encoders. Now let's have a look at the magnetic side of things. The next gen SoC is called iC-MUE. It's a magnetic off-axis absolute encoder solution. And it is kind of the successor to our very popular and successful iC-MUE family. But I have to admit, with a improved and very interesting feature set that I'm excited to present to you on the next slides. The iC-MUE comes in a 7x7mm QFN package. Our operating voltage and temperature range is the same as for the optical device I just presented. So 3 volts up to 5.5 volts and minus 40 up to 125 degrees C. The sensor technology, it's a Hall-based scanning principle, but it uses differential Hall sensors so that there is a proper robustness and tolerance achieved against magnetic interference and stray fields. It's also a 2-track scanning system, but it uses the Nonius principle to find an absolute angle. So there are 2 tracks on a magnetic pole wheel, which differentiate in 1 pole pair. So there is a phase shift of 1 track to the other. That phase shift is evaluated by the chip at startup to find a coarse absolute position. And then 1 track, the master track, is further interpolated on chip to increase the resolution. Key applications, well, this device is extremely flexible in encoder integration and use case scenarios. But one typical application would be hollow shaft encoders integrated into robotic joints, for example. Linear scanning is also possible with this device. On the feature side, the iC-MUE follows a platform approach. It can be the somewhat one-fits-all sensor component for complete encoder families. Why that is the case? The code wheel diameter is almost freely scalable up to 64 pole pairs. We call that decimal Nonius engine. So the number of pole pairs is programmable in the chip. If you want to go very big, if you have a large hollow shaft encoder or long distance linear scale that need to be scanned that exceeds these 64 pole pairs, you can extend one iC-MUE by a second one. This so-called 3-track system is capable of scanning a much higher number of pole pairs and so extends the measurement diameter or the measurement length. One major improvement compared to its predecessor, the iC-MUE family, is that all the outer adjustments are executed on chip. There is no external software required to calibrate the sensor whatsoever. These outer adjustments can be triggered either by sending a serial command over BIS or SPI, or by triggering a pin, for example, with a push button. One of the main motivations for this next-gen development was to increase the resolution and accuracy achieved with these hollow shaft magnetic encoder solutions. So the iC-MUE provides 21 bits of angle resolution with a 30mm outer diameter code wheel. But the accuracy is what's really impressive. So there is an integrated eccentricity compensation that compensates for this radial run out of the magnetic code wheel, and an additional lookup table correction that gets rid of all the remaining inaccuracies. Quite impressive results. I do have some measurement graphs on the next slides that really speak for themselves. All the relevant encoder interfaces are integrated in the iC-MUE, so the position data can be obtained by BIS, SSI, or SPI. The ABZ generator provides a programmable quadrature output resolution. We call that flex count, so the number of pulses per revolution is programmable. There is an additional sine-cosine output port that provides differential sine-cosine signals routed in a safety-ready signal path. And in addition, there is an absolute data interface, either to connect an external multi-trend sensor or to connect the second iC-MUE to obtain the 3-track system. Here you can see some examples of the iC-MUE combined with some magnetic scales. On the rotary side, there is classic axial scanning possible, but also these radial targets can be used with the iC-MUE. Of course, it can also scan linear scales, linear tapes. All of these magnetic scales have in common that they need to provide a 2mm pole width, because that's the pole pitch the sensor is designed for. I promised some measurement graphs, and here they are. So what you see here is the iC-MUE measured against the high-resolution optical device, the iC-RT2624 as reference encoder. Both are put into BIS chain, sampling the same axis at the same point in time. So on the y-axis, there is the angle error in degree, and on the x-axis, you can see 1 full revolution in degree. So this graph is what you would expect from an initially assembled encoder system. So the sensor was just put opposite the magnetic code wheel, and the absolute accuracy was measured here. So we start with plus minus 0.11 degree of angle accuracy. What you can see here is that a major portion of this error is coming from code disk eccentricity. So this typical long wave error over 360 degrees coming from the radial runout of the magnetic target. After executing the on-chip eccentricity correction, the results were as follows. So plus minus 0.04 degree angle accuracy. So the accuracy was almost 3 times better than the initial one. Already quite good, but what you can still see here is that there are some remaining inaccuracies. Might it be from magnetization or mechanics whatsoever. And you can get rid of that by using the lookup table correction against the reference encoder. And that's what I've done here in the next measurement. And I ended up with plus minus 0.01 degree angle accuracy with a magnetic encoder system. I think that number speaks for itself. That leads to my final slide for today. If you want to get started with either the iC-MUE or with the optical transmissive iC-RT2624, we have the complete evaluation ecosystem available. There are evaluation kits with the sensor, several different magnetic and optical targets that you can use. We would even have the motor with a reference encoder inside available, and an USB adapter to get you connected to our evaluation software to program and read out the chips. If you're interested, reach out at any time. And well, thank you so much for joining me today, and see you next time.
iC-Haus. Integrated circuits